Hello, Stuart Mason back with script 1C for Math 156. In this script we're going to import some data sets from the textbook website and take a look at how to kind of get a feel for a data set in R and make some top-level statistical observations about it. I do want to start by saying that I went back and looked at the YouTube videos of script 1A and 1B, and it looks like I kind of doinked up the visual quality. I'm trying something a little different with this one, and if it comes out much better, I'll be sure to circle back and redo 1A and 1B in a more visible manner. The first challenge really is figuring out how to get the data from the textbook website onto your computer and then into R. So I did talk a little bit about working directories in the previous script, and there should also be some helpful information on the course website about where to download this data. I'm going to assume that you've unzipped it and put it somewhere. For me, I took the resulting data folder and put it in my Math 156 folder on my desktop. So I'm now going to set my working directory there so that R can find all the data as Paul references it. So that's what this line of code that I added manually to the script is. I will quickly say that if you're not comfortable constructing this path in a text way, you don't quite know what the tilde means or where to start, we do have the option of using the File tab in RStudio, hit this triple dot button, navigate to wherever the data is, open that up, and use the gear to set it as your working directory, and RStudio will actually say, oh, you mean do this. So it's the same code that I wrote, but it's just that you don't have to construct the path manually. Great. So first thing we're going to do is read in this flight delays file, which is information about flights out of LaGuardia, and you guys know by now what the dimensions mean, how to find them, and of course n row and length are just kind of the individual pieces of that, and we can use the head function to grab a quick look at the top of the data set. And basically there's some information here about each flight that left LaGuardia in this time span, right? So what the flight number was, where it was going, when it departed. It's pretty self-explanatory. Nothing new so far. So we'll call the table function on the destination column to get an idea of where each of these flights is going, and if we bar plot that, we get this nice image that shows the frequency of destinations of flights leaving LaGuardia. Kind of interesting that Orlando dwarfs the others, but we can also make a contingency table from two factors, right? We can see whether or not it was delayed more than 30 minutes by the day of the week. We can take the mean and see, oh, it looks like on average when you fly out of LaGuardia, you're going to wait 12 minutes longer than you think you have to. The median's a little confusing. It actually comes out to -3 because so many flights leave just about on time, which means there must be a skew, and we can explore that with the histogram, right? So you see, yes, in fact, the vast majority of flights leave right on schedule, but enough flights leave, 2, 4, even 10 hours late, and that really messes up the mean. And this kind of shows you how summary statistics can be a little misleading. All right, and the next data set we have this sort of North Carolina birth data set, so let's read it in and take a look at the head. So it looks like we have information about the weight, gestation period, gender of the baby, and then some demographic info about the mother's alcohol and tobacco use and age. Cool. So we can make a histogram, and it looks like a pretty, symmetric, normal, centered right around 3,500 grams. We can take the sample mean, right, and the sample standard deviation, and compute the normal density function. We can plot it right over this histogram and get a sense for how a Gaussian approximates this histogram of our sample. Of course, it looks good to the human eye, but we'll learn some tools for how to see just how sort of expected or unexpected this behavior really is. We can use the split function to return a list by gender. So we're saying take the weight variable and split it up into a list by gender. So let's do that. Take a look at by gender, and what we get are two vectors, a list of two vectors, right? The first entry is called female, and these are all the female weights. And the second entry is called male, and these are all the male weights. Then we can use the lapply function, L as in list. So this is list apply. We're list applying the mean function, and we're doing it to the by gender variable. So every element in the by gender list will have the mean applied to it. And the result is that the mean of the female vector is 3398, and the mean of the male vector is slightly heavier at 3501. And we can even overlay the two histograms to get a sense for how the distributions vary. This is not a great way of doing this, as Paul points out in the comment. I have opinions, and I'm sure he does too, and I'm excited to share them with you later on. We can try to get a sense for if there's a relationship between gestation and weight, although there's so much data and so much variance that it's hard to see. So Paul suggests splitting out weight by gestation, taking the mean and plotting that. And then you see that, yes, on average, it does look like weight increases with gestation, although the relationship looks a little more complicated than linear, and clearly it's highly variant. Now let's take a quick look at some of the other data sets. So we have this Verizon data. This is the repair time in hours for problems based on whether or not the telephone carrier was Verizon's own or not. The interesting question here is, does Verizon take longer to repair other people's systems? Ideally, they wouldn't, and they're actually subject to a fine if they do. So it's interesting to note that the mean of the sort of non-Verizon set is 16.5, and the mean of the Verizon set is 8.5. So it does look like something's going on, but that could be the result of random chance, and we'll learn sort of statistical tools for answering how likely or unlikely that is to happen. Next, we have this sort of very large information about different demographics. People, looks like some kind of census. You see there's so many columns that kind of wrapped around several times. Let's take a look at the dimensions to get a sense for how many there are. So it's 2,765 observations. Each contains 21 aspects, so there's 21 columns. We can make it simple by tabulating just the politics, right? This tells us how many people identify at each political level. We can do contingency tables like you've seen many times by now, and you can see the relationship between owning a gun, not owning a gun, and different self-reported political values. We have this cool information about some student gathered information about how many hot wings each patron consumed, how many ounces of beer they drank, and what gender they are, and we can ask questions about the influence of gender on how much beer you drink, or the influence of how many hot wings you eat on how much beer you need to cool down. And finally, we have this spruce data set, which is the result of a researcher trying to influence the growth rate of different spruce seedlings over the period of 5 years based on different sort of treatments. So whether or not they were in competition, whether or not they're being fertilized, and we can ask questions about, does the height at year 0 predict the height at year 5, and yeah, it looks like there's a positive relationship. We can get the correlation. Maybe that's significant, maybe it's not. We can use tapply, as in table, to get the mean of the contingency table. So now we have sort of mean of the change based on whether or not it was fertilized and not fertilized. And it looks like, yeah, you do expect a height change of almost double for the fertilization case. We can ask the same thing about competition. And it looks like we can even supply a list to make a sort of a mean by contingency table, which is again what the T stands for here, right? T as in table. Cool. So that was a quicker kind of romp through. This was a pretty self-explanatory script, but I'm also trying to cut down because the first two did come out quite long, and I do want these to be watchable. Great. So hope that was helpful. Feel free to reach out to me with any questions if it was too fast, or if you're having trouble with the work directory stuff, because I really do think that's the only challenge of this script. And I look forward to talking to you guys in 1D.